Hi everyone. In this video we're going to be going over some modern physics concepts. Specifically we're going to talk about the classification of matter and the particles of the Standard Model. So I want to start by looking at what we typically think of as a diagram of an atom. We see a nucleus with protons and neutrons, and then we see electrons that are orbiting on the outside. And I want to think about three questions. The first question is, where are protons located in an atom? Then, are they close together or are they far apart? And finally, will two protons attract or repel each other? So if we answer these questions based on our prior knowledge, we know that the protons are located in the nucleus, which is the center of the atom, and we can see that they are really tightly packed in there. They are very close together. In the electrostatics unit, we learned that two protons will repel each other because like charges repel. So if we think about it, it doesn't really make sense that the neutrons and the protons are packed in so tightly into the nucleus, because why wouldn't the protons just want to be as far away from each other as possible? So something must be holding those protons together. And that's where we learn about some new forces that we haven't really talked about yet. So there are four fundamental forces that exist between particles, and they're listed here in order from weakest to strongest. Gravitational force shapes the large-scale structure of the universe. So you'll see that with galaxies, stars, and planets. When we learn about gravity, we're learning about it with the attraction of the Earth to the Sun, or the Moon and the Earth. So really big objects, and it has a really far range. Then the weak nuclear force, that is for radioactive decay and nuclear fusion. And for the physics regents, you don't really have to worry about that. Electromagnetic includes electrostatic and magnetic forces, so we've learned about electrostatic forces a lot, and many of us have some prior knowledge of magnetic forces if you've ever played with magnets. But today we're going to talk about the strong nuclear force, which holds the nucleus of an atom together, and it has a very short range. So it literally only works inside the nucleus of an atom. It won't work anywhere else because it can only work over such a short range. So basically, all you need to know is that the strong nuclear force, which is sometimes just called the strong force, holds the protons and neutrons together. And that's basically it. Next, we're going to talk about how we can classify different types of matter. So matter is either a hadron or a lepton. No matter what type of particle you're looking at, it can be called one of those two words. Now, if it's a lepton, there are 6 leptons that exist. So, for example, an electron, that is classified as a lepton. The rest of these you might not have heard of: muon, tau, and then electron neutrino, muon neutrino, and tau neutrino. They might just kind of sound like random words, and the truth is you don't need to know much about what they are or what they do. You just have to kind of recognize the word and be able to look it up on this chart. So if you see any of these words, you have to look it up and you'll know that it's a lepton. These particles can't be broken down any further. But you can also have hadrons. Now hadrons come in 2 types, but both types have to do with these particles up here, which are called quarks. So you might have a baryon, which is made up of 3 quarks. So for example, you could have up, charm, top. Those would be 3 quarks that might make up a baryon. You could have down, strange, charm. You could have up, top, bottom. And they can repeat. So you could have up, up, down. Or you could have charm, charm, strange. Or any, really, literally, there's millions of combinations. So whatever combination of 3 of these would count as a baryon. You could also have a meson, and that is a little bit more tricky because it says it's made up of a quark and an antiquark. You have to see this tiny note down here that says for each particle, there is a corresponding antiparticle with a charge opposite that of its associated particle. So that means if I see an up quark, there also exists something called an anti-up quark. And it, instead of having a positive 2/3 charge, it has a negative 2/3 charge. So I just kind of imagine that each of these little boxes is like a card, and I could flip the card, and there's the antiparticle on the back. So on the front, it's a positive 2/3 charge for an up quark. If I flip that imaginary card over, Now it's an anti-up quark, and it just has a negative 2/3 charge. So you just have to kind of remember that they're there and that they exist. So a meson could be down, anti-strange. That would be a meson. Or a bottom and an anti-bottom quark together. That would be a meson. Protons and neutrons are examples of baryons. So they are made up of 3 quarks. A proton is up, up, down, and a neutron is up, down, down. Sometimes it'll be written like this. Actually, this one is most common, just the first letter of each quark. So UUD and UDD. That is something you're going to have to memorize. You have to know the quark composition of the proton and the neutron. It might come up on the Regents. So for the chart, the directions are to calculate the charge for each particle, then check as many of the boxes that apply. So for example, this stands for up, up, down, so it's a combination of 3 quarks. I'm going to look at those quarks on my reference table, and I'm going to see that up is positive 2/3 and down is negative 1/3. So when I go to calculate the charge, I'm doing plus 2/3, another plus 2/3 because I have 2 of the up quarks, and then a minus 1/3. I can put that in my calculator and it should give me positive 1. When I write that in the chart, I'm writing plus 1e because both of these charges have the unit e for elementary charge. So it's positive 1 elementary charges. Now I have to check off however many of these boxes apply. So is it a baryon? If it is, I'll check it off. Is it a meson? I'll check it off. So I'm going to look back here, and I see that it was made of 3 quarks, up, up, down. So it must be a baryon, which means it must also be a hadron. And then I can eliminate meson and lepton. So I'm just going to check off baryon and hadron and leave these 2 blank. And then in my next row, this C with the line over it stands for anti-charm quark. So anything with the line over it is the antiparticle. So you can go ahead and look up the charge for each. Remember, for the anti-charm, you have to flip the charge. So a charm quark has plus 2/3. The anti-charm is going to have a minus 2/3. And then look up the charge for the strange quark, add them up together, and then check off whichever of these apply.